Okay, today I want to introduce BCS wave function. Luckily you didn't miss much. I think you missed some good portions, but still there's the best part is still yet to come. So let's talk about BCS wave function. So what did we see last time? Last time we saw electron-electron interaction plus screening plus phonons can conspire to give a tiny but non-vanishing small attraction between electrons, like weak attraction between electrons, right? This is not very easy to understand because electrons generally repel each other, but in the complex environment of solids, we argued there is a way to do this. And the second thing was so-called Cooper, sometimes people called Cooper's theorem, and arbitrarily small interaction, small attraction gives bound states. And we said this is also like unexpected because in three-dimensional space you need to have like a certain strength of attraction to get a bound state between two quantum particles. Therefore, from here we deduce if there is like bound state for two electrons, there is bound state for all electrons, right? That means around the Fermi surface, all electrons should pair. That means Fermi surface is unstable under pairing. And now the job is, if this happens, we should be able to describe this with a wave function. So another way to say this is like because all of these electrons pair and do some kind of Bose-Einstein condensate, we should be able to write a coherent state for this. So we need a coherent state. And we argued that this is actually not easy to write, right? Because bringing two electrons together doesn't just make bosons, because these electrons are overlapping. So, but we will see this can be done. To do this, first, let's assume translational invariance. So that K is like a good quantum. And I want to introduce so-called pair creation operator. So this is pair creation. Let me use P, but at some point I'm going to forget putting heads. But let me try. P of K is going to be, you create one electron at K with spin up, and you also create another electron with zero center of mass total at minus K and down spin. So these are fermion creation operators with the anti-commute. And the required coherent state was actually written by Schrieffer. Let me write it, and then we are going to be talking about that a lot. So the coherent state so let me call this psi BCS, is similar to what we had for bosons, but there's like some arbitrary constant, And I think I need to open up some space. Minus sum over all k, some complex alpha, exactly like what we had for bosonic coherent states, times this pair creation operator, pk, and this entire thing is acting on 0. And in the following, we are going to assume these alpha are complex variational parameters. So that means we'll determine them in such a way to minimize the energy. And this 0 is vacuum with no particles in it. So this is formally similar to bosonic coherent states, but it is not that straightforward, right? The reason is, okay, I think you asked this last time. Let's go through one more time. So this pk prime, so these are operators, right? So this is like 2 electron operator here and 2 electron operator here. They anti-commute, and every time you switch one, you get the minus sign, but you switch 2, so in total you don't get a minus sign. So then this one is 0, so that this one. So there is no problem with this. I think last time you were asking this, right? So there is no problem with that. But we don't want anti-commutation. Here we want commutation, because these are bosons, and here we have C, here we have C, like these are different indices if you want. Because I don't know, I, J, I don't know, K, L, because indices are different, this guy can commute to here, first picks up a minus sign, commute to here, another minus sign, which is plus. You can commute to here, and then here, another, and then they just commute. So this one does not have a problem. The problem is the other one. If you have something like that, P dagger, that's the problematic one. And I want to spend just a little bit time on this. Let's take pk and k prime to be the same, and let's calculate, because I think at the graduate level, I think it's not too much to ask a little bit of skill to manipulate these like second quantized operators, right? All you need to do is just keep track of ordering and the signs, and that's actually the most tricky thing for undergrads, right? So let me just spend just a few minutes to maybe at least do this calculation. So this is what? This is C minus K down, C K up, commute with C K up dagger, C minus K down dagger. But this is what we want to calculate.
I think there is something wrong with our definition of
Piece. Let me see. I may be like missing something. So this is the P, right?
There should be P dagger.
Oh yes, absolutely. Thank you. Yeah, that's P dagger. Yes. I think this is also P dagger. Yes, that's correct. Thank you. I think it's okay now, right? Mm-hmm. Yeah. Okay. So what I will do is, I think I can just write and then look at the results. So this is this thing times this thing minus this thing times this thing. And let's look at this piece. This is so the anti-commute, right? I'm going to write for this 1 minus CK up dagger CK up, right? Then this thing is going to be this and this comes from one piece, right? This one is taken care, minus this times the second term times this last term. And so I'm trying to put this in the same order, so this term and this term I can cancel. So I need to do one more. So these two, they are different case, so they also they also commute with a minus sign, right? These are fermionic operators. So I can do this and make this plus now. So this one is now plus. And I can also do this. So this can also go to here. There will be one more minus sign. So like this. Now this is minus. And now this is ck. So I will do the same thing. This is going to be 1 minus c minus k dagger. C minus, okay, there is also spin. C minus k dagger down. C minus k down, and that means, okay, let me write. So this is equal to, I'll have this is first term, I didn't touch it. So this is the second term coming from the this one, and lastly this minus and this minus is going to be plus. So this thing, okay, this is plus this thing. Good. And now I can just, okay, what is this order here? K minus k minus k k. So k, I can change the order, right, again like this. So this one is going to go, okay, is that, this one is going to shift like this, and I'll have this back here. So this is now minus. So this is k minus k minus, I need to change one more time, right? This is also not like this, and this is now plus k minus k minus k k, k minus k minus k k. Okay, now, so this is plus, this is minus. I can cancel this term with this term, and this one I'm also going to write it in the normal order. This is equal to 1 minus, right? C dagger C is number operator, so I'm going to call it n minus k down. This is also minus n k up. But the important thing is this commutator. So this is equal to that, and that's not a simple bosonic commutation, right? So that's the difference from the bosonic coherent states. Good, but nevertheless, right? They may or may not commute. It's okay. I mean, they are not proper bosons, but I can still define this, what I call the BCS wave function, as a variational wave function and try to calculate things, and that's what I'm going to do today. So since we are already here, let's also calculate this thing. So this p k dagger, if you apply it twice, this is pk dagger squared, and it's going to be c k up dagger c minus k down dagger times itself. But what is, so these are fermionic operators. What is the operation like this for any fermions? If you have C dagger, or if you have CC, what is the result? 0, right? Because you cannot create two fermions, so this is 0. So now I'm going to use this to manipulate this BCS wave function. So this is psi BCS is equal to some constant times exponential sum over OK, alpha k, pk dagger acting on 0. So these different pk's, they commute, so I can decompose this. I can decompose this like a product. I think everybody knows this Baker, Hausdorff, Campbell formula, right? If the things commute, exponentials can be split. So this is going to be a product, sum over exponential of sum is going to be product of exponents. And this is e to the alpha k pk dagger acting on 0. And now these are operators, and we know operators are defined by their Taylor expansion. So this is going to be product over k 1 plus alpha k pk dagger plus alpha k star pk dagger square dot 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 acting on 0. But we just showed, right? We just showed square of this pk dagger is 0. All these higher terms are not going to contribute. Therefore, the BCS wave function is going to be identical. So this coherent state for fermions is identical with a little bit of simpler form like this: 1 plus alpha k pk dagger acting on 0. Okay, so this is beside BCS. Any questions?
I mean, we can write this for any harmonic system, right? So
Yes.
it's not very special to BCS.
Yeah, it is not very special to BCS. Yes. So as a variational wave function, actually people use it for other systems. But in our context, in the context of superconductivity, it is going to correspond to pairing.
Okay.
And we are going to see if the pairing is 0, these alphas are going to be 0. Not alphas, but we're going to rewrite this, and this will have a certain form when there is pairing and another form when there is no pairing. So now I want to normalize, so I want to write this in a normalized form. Let's consider psi BCS, psi BCS going to be equal to this is each term, right? I can take the product of each term separately. So this is going to be norm of c squared. So, and let's also take product over k. This is 0. So this is 1 plus alpha star k pk and 1 plus alpha k pk dagger 0. So these are operators. So I'm just curious, how many people know knew second quantization prior to this course? Like this, right? You know it a little bit, but I don't expect too much, right? We just have operators. If you've never seen this before, it's a little bit, I know, uneasy, but we don't need too much. We just need to feel a little bit comfortable. So this thing is what? So I can have like direct terms, 1, 1. So I can have this and this, that's fine. If I have this and this, I have things like this: 0, some coefficients times p dagger 0. What is this? This is 0 because you create fermions on vacuum and you go back to vacuum. They cannot have like an overlap. So this one is 0. Similarly, this one is also 0. What comes out is only the this 0. I think I put the product outside. This is 1 plus alpha k squared pk dagger 0. Yeah, maybe I can also do this calculation because we are going to need the skills to manipulate these operators. So the goal is, right, we want to have annihilation operators hitting on vacuum so that we can set them 0. So that's why we like things in normal order. So let's think about this. pk dagger acting on 0 is going to be equal to ck up, actually minus k, ck down, ck up dagger, c minus k down dagger acting on 0. So the goal is put all the daggers to the left of no daggers. And minus.
Don't have the same spin.
Oh yes. So this is minus k up.
K down, and there should be K down as well.
I think this is like yes. This is, I think like this. K down, up, down. Right? This is now correct. I think. Down, up, down. Minus k, minus k. Okay, thank you. So this piece is going to be 1 minus ck up dagger ck up. Now this ck is to the left of this c. That's good, and it's going to be equal to the same calculation, right? I have this piece and this piece. Minus again this thing and this thing and this thing, and this one is going to be 1 minus c minus k down dagger c minus k down. Now c, right, this c is going to hit on this 0, so I can just kill this. So this, I'm going to kill it. And I have here the same thing. So this is k up minus k down. So I can just commute this. And there'll be like a minus sign. It's going to be a plus. But once this c is acting on 0, it's going to be 0. So there's only 1 left here, right? Therefore, this pk dagger 0 we found to be 0. And we can use it here. From there we see this psi BCS is equal to this c squared product over k 1 plus alpha k squared. Now I can push this c inside, but another way to do the same thing with a little bit nicer form is like to define BCS like this. From here, BCS is equal to product over all k. I have uk plus some vk ck up dagger c minus k down dagger acting on 0, and uk is 1 over 1 plus alpha k squared, and vk is alpha k over 1 plus alpha k squared. And I can also put here an arbitrary phase, like something like I theta k. But at the moment it's not important, but in the future it will be important in some problems. For the moment, let's just not make things look complicated. So this is the BCS wave function, and you can see this is uk square plus vk square is equal to 1 coming from there, and we will use this form of variational wave function. Good. So this is right. This is one of the famous wave functions. Like you said, people use it in other things, but in physics, I don't know many variational wave functions. But there is another context. I think in the fractional quantum Hall effect, there is like Laughlin wave function. In the BCS context, there is BCS wave function. There is a couple of more, but nothing is as strong as these two wave functions, right? And it is like actually not very easy to, even on the variational level, it's not easy to write a good wave function. And these two examples, right? BCS wrote like a wave function, they got the Nobel Prize. Laughlin wrote a wave function and he also got the Nobel Prize. So it's like very tough to come up with these things. And the reason is, so this thing you can see is not conserving the total number of particles, right? This is like a coherent state. So this is a coherent state with n particles, n plus or minus 2 particles, n plus or minus 4 particles. And people didn't like that in the early days. They were like, okay, where are these electrons going, right? Today we don't have a problem with that. We don't have a problem because we know there is like an uncertainty in number of particles, and this is proportional to root n. And this is not a problem because delta n over n is 1 over root n, which goes to 0 as n goes to infinity in the thermodynamic limit. And we understand these things, right? We even connect this to like symmetry breaking. Good. Okay, let's continue the program. So the goal now is to find these complex parameters UK and VK by minimizing energy, like expectation value of Hamiltonian. And the Hamiltonian we are going to use is, of course, is going to be this weird Hamiltonian we tried last time, and it was something like that. So this is H, sum over all momenta and spin, some energy dispersion, which is going to be h bar squared k squared over 2m, but let's keep it like this, c k sigma dagger ck. There is nothing weird about this. This is usual quadratic fermionic dispersion. But the second piece, we said after all these discussions, there is like a minus g effective square. There is like a minus sign of attraction, which means these electrons are attracting each other. And the form of the Hamiltonian is something like this. This is k prime. So this is c k up dagger, c minus k down dagger, c minus k down prime, c k prime up. So that means, so here's my Fermi surface. I have one pair, so this is minus k, let me call it down, so this is k up, and they are paired, and they, after this interaction, they scatter to another pair. I don't know, something here, another one here. This is k prime up, so this is minus k prime down, so they still paired. And this is only describing this process, right? and nothing else. And the job is, given this dispersion and G effective, find U and V so that the energy is minimized. So the program is define this energy functional if you want. So this is UK VK is equal to psi BCS H psi BCS. But we also have constraints. One constraint is, okay, we need to have for each k, u squared plus v squared is equal to 1. So this is the normalization we just derived. But there is also a second constraint. We also need to have mean number of particles, n without any head is defined by expectation value of number operator to be also constant, right? We want to do this in like a given n. So these are constraints, and we are going to define Lagrange multipliers for these constraints. Okay, maybe I can do a couple of preliminary calculations, and we can do the good part next time, right? So this is a big program, right? So we have C dagger here, and even worse, C dagger CC here, and we are going to hit this Hamiltonian on this wave function, which has U plus V C dagger, and we will have to move a lot of C daggers to the left of a lot of C's. So let me start with expectation value. Okay, let's start in little pieces. Let's start calculating expectation value of nk, and let's only take k up, right? I'm not even talking about this gigantic Hamiltonian. I just want to put this thing, like this is BCS, so this is C k up dagger, C k up, so this is psi BCS. All right, so let's write. So what will happen is there are many products of k's, right? So this is the wave function. There are like many products of k's, and all different. If the k here is different from the k I picked up here, they just all go through, and they are all already normalized. There's nothing to do about them. So we all only need to pick this k, right? So this is 0. So just take this guy with the correct k here. It's going to be something like this. In the bra side, it's going to be uk star plus vk star c minus k down c k up. So I wrote the bra part. Let me see if I wrote it right. Minus k down, k up. Yes, I think that's correct. Now this k, c k up dagger, c k up. And the ket part. So this is going to be uk plus vk ck up dagger, c minus k down dagger, acting on 0. Now you can see, right? So there is going to be, so UK, this term, UK, right? Let me try to highlight which terms I'm talking about. This term is going to multiply this term, and it's going to multiply this term. It's going to be something like U square, but C dagger C acting on vacuum is 0, right? Like there will be a lot of zeros. It looks terrible, but sometimes we have to manage our psychology and say, okay, I'll do this. So this is 0. And similarly, if I have this term, so this term, and this term, and this term, I have C daggers, right? 1, 2, 3 C daggers, but only one C. So you are hitting on the vacuum with 3 C daggers, but you are still contracting it vacuum, so it's also going to be 0. Yes?
Earlier we defined the number operator to be C dagger, not C daggers.
So this one, right? Let me fix that. So this is, I think this, are you talking about here?
Yes.
Yes. So this C dagger C is number, that's correct.
Okay. Yes.
And this, I commuted this and put 1 minus. Yes, yes, good. So what I'm trying to say is like, so the only term is going to be this term, right, and this term. And the reason is I have like 2 C's here, which is going to pair with 2 C daggers here, and it's going to give a good thing on the vacuum. And I have C dagger here and C, and everything will match up. And I don't need to calculate anything else. So it looks terrible, but there's already drastic simplification. So this is going to be equal to VK squared 0. Now we are going to have C minus K down, C K up, C K up, C K up, C K up dagger, C minus K down dagger. Yes, this one I missed. Is that okay now? Right? C dagger C, C dagger C, C dagger C dagger. Okay, that's good. Minus K, minus K, K, minus K, K minus K, and it's going to be down, up, down, up, up, down. Yes, I think everything's fine. I think there are also like easier way to do this, but I want to follow the book, because book gives like a systematic prescription, and the rule is move always daggers to the left, and when you hit with C, it's going to be 0. So let me pick this piece. So this piece is going to be 1 minus C K up dagger C K up, and then what will remain is like this piece times this one times this minus, so this piece times this, oops, try to take it, times what is remaining is here. Okay, so let's look at this. And now I see this, right? This is CK up, C minus K down. I can commute this safely, there's no problem with that. And then I can take it here, and there will be a minus sign here, which is going to make this minus plus. But now this CK is acting on vacuum, so this entire thing is gone. So we already had like drastic simplification. Even simpler, right? We are getting a little bit more hopeful. And let's look at here. So this is K up, K up. So first I need to commute this one to 1 minus, so this is 1 minus CK up dagger CK up. So the result is going to be this thing times 1 times this thing, oops, and minus the same thing like this, this, and this. And now you can see this is K up, this is K down. I can also commute this, like here. And this thing is going to be plus, but now C is acting on vacuum. This is also 0. So what remains is C minus K down, C minus K down, and I'm going to do the same trick. So this is 1 minus C minus K down, dagger, C minus K down. But C acting on vacuum is 0. At the end, all this mess turned out to be just 1, right? Which is nice. Therefore, what we calculated is expectation value of C, K up, or let me write it like N, K up is simply, what did we find? Vk squared. Good.
Can you ever get something that's not plus minus 1 in like?
Yes. I don't know if we'll have time today, but next time we are going to calculate pair operators expectation value, right? So we are going to calculate C minus K up, C K down. So this one is not going to be like this. But at the end, you always get this, right? You always have a sequence of C's and C daggers, and there is always equal amount of daggers and no daggers, and you are always there is something called Wick's theorem that I'm trying not to scare anybody, but it is a way to do these things very systematically. But if you want to do it like without knowing anything, this is to do this, and you always get 1, right? At the end, you commute things. C's are going to act on vacuum, and you always get 1, right? So that's the Wick's power of Wick's theorem. So let me try to see where this is going. Okay, this is what we had. So let me write then, right? So this gigantic N, which is the expectation value of sum over all K, CK up, CK up, dagger. We also need to think about spin, right? There is like CK down, dagger, CK down, acting on 0. But here, right, there is nothing that makes this up spin special, right? We could do exactly the same calculation for down spin, and because up and down is our labels, the results should not change, right? If you have any doubts, I invite you to sit down and do it, and it may be a good practice for you to develop these skills. But at the end, this one is going to be V squared, this one is going to be V squared, and this entire thing, let me call it N without head, is average number of particles, which is going to be this 2 times sum over all K Vk squared. This we are going to use later.
Don't be a graph with this equation.
Oh yes, I think this is 0. Okay, yes. So this is what we get. We can also consider now kinetic energy, right? So the smallest piece is all we want, right? And we did most of the work already. Now we can also calculate expectation value of kinetic energy, which is going to be expectation value of K and sigma, epsilon of K, C K sigma dagger, C K sigma expectation value. But this is exactly the same form. Then I'm going to write this K as, maybe I ask you, what should, if N is given like this, what should K be?
2 summation epsilon K B K.
Yes, exactly. There is no difference. So this is like that. And I'm just going to put epsilon of K here.
Hocam,
Okay, maybe
Is these rules are true? Is it correct because we are looking at BCS wave? Yes.
Yes, like yes. I think I messed up. Yes, you are right. So this should be BCS. So this one is BCS. This one is also psi. If you hit on 0, you are going to just get 0, right? That's, yeah, thank you. And this one is also BCS. If you want, I can put BCS expectation value here. Okay, let me leave the better part for the next time. So next time we need also define this V interaction, which is written here. So this is that. It also looks horrible, but you know, once you keep your faith and do the calculation, it comes out very simple. So this is what it is, and we need expectation value of V in the BCS wave function. Once we do that, we have like some energy as a function of these variation parameters U, V, actually U, K, V star, because these complex conjugates and numbers are independent, UK, VK, and we are going to do the minimization, functional minimization if you want, and it's going to give us something like Gross-Pitevsky equation, but it is for superconductors. And we are also going to look at Bogoliubov modes and things like that. Everything will be a repetition of what we already know, but it will be a different reincarnation. Okay? All right, thank you.